So welcome to the NCGT seminar, and it's my pleasure to introduce Eduard Vilalta from.
Okay. So thank you very much for the invitation. And yes, as you said, I will talk about soft elements in sister algebra, which is based on joint work with Hannes Thiel. And hopefully, if time allows, I will also discuss some of the things that I've been doing with Alias Adibasfi and also Hannes. Actually, some of these results I got when I visited here last year. So let me start with an introduction. So this is section 1. And I should mention that I recently gave a talk in Barcelona with a slightly different name, but which essentially contained the same results that this talk was. The difference is how I'm going to be presenting the results. And one of the main differences between that talk and the one that I'm giving now is in the introduction. Mainly because back in Barcelona, something that I said, which is still true today, is that the goal of this project was twofold. So there is a notion of softness for Kunz classes. And something that we wanted to do is to produce a sister analog for this. So given a positive element, one can construct its Kunz class, which is something that I will recall. And then there is a notion of softness for this object. And surprisingly, even though this has been around for 5 or 6 years, there was no sister algebraic analog for this. So given a positive element, you can study if its Kunz class is soft, but there is no notion of that element being soft in sister algebraic terms. So that's one of the things that we wanted to do. The second thing is that although this is defined generally for any sister algebra, it's only truly in use for stable rank 1 sister algebras. So a legitimate question is to say, well, when we don't assume stable rank 1, is this still the right definition, or should we change it slightly so that it works better? And so the second thing that we wanted to do was to provide the general definition for this. Oops. So this is something that, as I said, I mentioned in Barcelona. And another thing that I said there was that the reason why we wanted to do this is because there are plenty of situations where these elements appear natural. And even though I claimed that back then, I never gave an example. And Loran and Karen can testify to that because they were there. So in some sense, to amend that, I'm now going to give an example where these elements appear. And so the introduction is going to be on the rank problem. Which is an open problem for sister algebras that's related to the Thomson conjecture, or at least the remaining implication of it. So just to recall what that is, even though I assume that most of you have heard the name, this is a conjecture for certain simple sister algebras that predicts that 3 conditions of different flavor coincide. So explicitly, what the Thomson conjecture says is that given a separable simple nuclear simple unital sister algebra, and which is also non-elementary, then the following 3 things should be equivalent. So following equivalent. The first one has, in some sense, a topological flavor, and it says that A has finite nuclear dimension. And when I say that it has a topological flavor, is because one can understand the nuclear dimension as the non-commutative analog of the Lebesgue's covering dimension. The second one is somehow analytical, and it says that A is Z stable. Meaning that it absorbs the Jiangsu algebra tensorial. So and the last one is a condition in the Kuhn group, and so in some sense it's an algebraic condition. So third one says that A has strict comparison. So as I said, what the conjecture predicts is that these three things, which seem to be different at the same. And so, well, if you've heard of the Thomson-Weinter conjecture, then you probably also know that this conjecture is by now largely a theorem, meaning that we know all the implications except one. So by now, what we know is the following. Going in chronological order, the first thing that we knew was that 2 implies 3. So that stability implies strict comparison. And this is largely due to Jordan from 2004. And this was actually known way before the conjecture was stated. So this is something that people were already familiar with. The second thing that we knew was that 1 implies 2. That finite nuclear dimension implies that stability. And this is result by Vinta from 2014. And not only do we know this, but we actually know that 1 and 2 are the same. So it's also known that Z stability implies finite nuclear dimension. And well, there are plenty of papers on this, but let's say that the final theorem was given by Castillejos, Ebbington, Equizis, White, and Vinta. This is from 2020. So as you can see, we know that the first 2 conditions are the same, and that any of these 2 implies the third. So all that's left to prove is that the third one implies one of the first 2, mainly the 3 implies 2. So what's left is that 3 implies 2. So in other words, that strict comparison implies that stability. And where does the rank problem appear? Well, it turns out that there is an approach to 3 implies 2 that uses the Kuhn group. And that's where the rank problem is going to appear. So a possible approach which is not the only one, so 3 implies 2, uses the Kuhn group. But again, as I said, this is not the only approach. For instance, one can use uniform property gamma, and there is some intersection, but it's essentially a different thing. So, okay. Yeah. I'm going to define it at some point in the introduction. Yeah, exactly. It's a thing that's defined using the Kuhn group. So before defining strict comparison, I'm going to define the Kuhn group, but then I will get to the strict comparison. So, okay, let me recall what the Kuhn semigroup is. And in order to do that, and I always say the same thing, but the basic idea behind the Kuhn semigroup is that it generalizes the Murray von Neumann semigroup. Or the Murray von Neumann semigroup is the semigroup built using projections such that its abelianization is the K0 group. And so the simple but great idea behind the Kuhn semigroup is to copy the definition of the Murray von Neumann semigroup by changing projections for positive elements. And essentially, this is done because you always have plenty of positive elements, even though when you don't have projections, right? So the definition, as you'll see, just mimics what one does when one defines, let's say, the K0 group of a sister algebra. So given a sister algebra, then the Kuhn semigroup is the following quotient. So you take all the positive elements in the stabilization of A, instead of taking the projections, which is what you do for the K0 group, and you quotient this out by an equivalence relation, where this equivalence relation is the symmetrization of subequivalence relation, and I swear that this is going to make sense, with this subequivalence given by the following definition. So a positive element in A tensor K is subequivalent to another positive element in A tensor K, if and only if, by definition, A is the limit on N of Rn be Rn star for some sequence Rn in A tensor K. Okay. So we say that A is subequivalent to B if this happens, and then we say that A is equivalent to B if A is subequivalent to B and B is subequivalent to A. And this turns out to be an equivalence relation, and so this is a legitimate quotient you can consider. And as in the Murray von Neumann case, we equip this with an order and an addition. So we equip Cu of A with the order induced by the Kuhn subequivalent. So we say that A is less than or equal to B, A is subequivalent to B. And the addition is given by diagonal addition, like in the K0 group. So A plus B is the addition induced by looking at this diagonal. And this is one of the reasons why we work on this stabilization. It's not the only one, but it's one. So, okay, this turns out to be an interesting invariant for sister algebras. And as I said, a possible approach to this remaining implication uses the Kuhn semigroup. And so to use the Kuhn semigroup, we already have the third condition stated in Kuhn semigroup terms, which again, I'm going to recall what the definition of strict comparison is. But if we want to use the Kuhn semigroup to approach 3 implies 2, we also need a characterization of 2 in terms of the Kuhn semigroup. And this was given by Vinta in 2012. So what he proved is Vinta 2012 is that if you have a separable simple unital sister algebra of locally finite nuclear dimension, and I will comment on this in a second, then what you get is that being Z stable, so observing the Jiangsu algebra tensorially, is the same thing as this happening in the Bunsen group. So this happens if and only if the Bunsen group of A is isomorphic to the Bunsen group of A tensor Z. And well, if you want me to give the definition, I can give it to you of locally finite nuclear dimension. But essentially, what's relevant is that there is no known example of a separable simple unital nuclear system algebra that does not have locally finite nuclear dimension. So presumably, this is the same class, even though, of course, I guess that the proof is something very difficult. But yeah, for now, you can just assume that this is a complete restatement of condition 2. So now what we have to prove is that strict comparison, whatever that may be, implies this. And this, again, is where the rank problem comes in. Essentially, the two relevant things that I'm going to discuss now have something to do with linear algebra, with vector spaces. So in a vector space, let's say B, the set of functionals of this vector space form another vector space, which is the dual of B, right? And since this is another vector space, you can apply the construction again and get the double dual. And the thing that I'm going to focus on is that given any element in B, there is a natural way of assigning it an element in the double dual, which is its rank, right? So given B, you can send this to something that's called the rank of B, which is mainly the map from B star to C that sends each functional to the evaluation of B of that functional. And that's an element of the double dual. And by the things of linear algebra, this is an isomorphism actually from B to B star star. Now, the rank problem has to do of studying what happens when you change B for a Bunsen group. Then there is something that looks like the dual of the Bunsen group, even though it's not a Bunsen group. And there is another construction that looks like the double dual. And there is also a natural way of sending an element of the Bunsen group to its double dual. And that's where strict comparison is defined, and also the rank problem. So to define strict comparison, the first thing that I need to do is to define what the dual of a Bunsen group is going to be, which again, it's not called the dual because it's not a Bunsen group, but it's informally what the dual of the Bunsen group should be. So we will say that a map from Cu of A to 0 infinity is a functional if it preserves order, addition, and suprema of increasing sequences. So just like one has a notion of functional for vector spaces, this is the notion of a functional for a Bunsen group. And as I said, the set of all functionals is not a Bunsen group, but still we think of it as the dual of the Bunsen group. And so we denote by f of C of A the set of functionals. Now, what's strict comparison? Well, strict comparison is a property that's actually automatic in the setting of vector spaces. So when you have a vector space and you take two elements, then if they agree on every functional, then they are the same. Simply because you take a basis and you can take a functional that sends that element to its coefficient of that basis, right? But now in Bunsen groups, that's no longer the case. And even a weakening of it is not true always. And that weakening is what we call strict comparison. So it's a property that sometimes holds and sometimes doesn't. Mainly, one says that CU of A or A has strict comparison and well, for the record, I'm always working with simple sister algebras in the introduction. But we say that A has strict comparison if an element X in the Kuhnsen group is bounded by another element Y whenever lambda of X is below lambda of Y for every functional of the Kuhnsen group, and such that this inequality is strict when this can be strict. So for every and lambda of X is strictly less than lambda of Y whenever lambda of X is not infinite. So if lambda of X is infinite, you want lambda of Y to be infinite, and if it's finite, you want this to be strict. So again, this is something that happens automatically for vector spaces, but for sister algebras, this is no longer true. And so this is a property, and that's what we call strict comparison. So that's strict comparison. Can you still see this if I move it down here, or should I just put this here and use the other ones? Yes? Okay. 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 So now, continuing with these analogies for vector spaces, what we can now do is produce a double dual, which again is an informal double dual. It's not an actual double dual. And so one can define, one defines L of F of CU of A, which again, informally, this is CU of A star star, as a subset of the maps that go from the functionals to 0 infinity. So yeah, I'm not going to give the precise definition because the details get slightly tricky, but the key thing is that you can think of it as the double dual, because it truly takes elements of the dual, informal dual, and sends it to 0 infinity. What's important here is that we still have that rank map. So given an element X in the Kuhnsen group, the map X hat, which goes from F of CU of A to 0 infinity, and takes a functional and evaluates it at X, is in this informal double dual. This is always here. Is in L of F of CU of A. So now we are exactly in the same setting as in the case of vector spaces. But now, again, as with a strict comparison, something that was automatic for vector spaces is no longer automatic for Kuhnsen groups. Mainly, the rank map for vector spaces was surjective. And this is unclear for Kuhnsen groups. And that's what the rank problem is. The rank problem asks when this map, sending X to X hat, is surjective. So, problem, and this is the rank problem. When is X to X hat surjective? Now, how is this all related? Well, it turns out that the positive solution to the rank problem is the same as 3 implies 2. Assuming locally finite nuclear dimension. So say theorem. Let A, and this is, I guess, also. So let A be separable, simple unital system algebra of locally finite nuclear dimensions. And assume strict comparison. So mainly assume that you are in 3. Then the following character. 1 x to x hat is surjective. And 2 cu of A is isomorphic with cu of A. So by what I've just stated before, this will imply Z stability. So it will follow that 3 implies 2. And so that's the connection between the rank problem and Z stability. And well, of course, the question is now, well, what has softness, to do with all this? And this is where soft elements will appear. Mainly, when you solve the rank problem, elements that are soft, which I will now define, appear in a very natural way. So arguably the biggest advance in this sort of approach, in the rank problem approach, was done by Thiel for the simple case. So simple meaning simple system algebras, not easy. And then Antoine Pereira Robert and Thiel for the general case. It's the same thing. Simplicity of the Bunsen group is the same thing as the system algebra being simple. But yeah, I mean, yes, always, if I say simple, I usually mean the system algebra, but it's the same thing. Okay, so what they proved is that if you have a stable rank 1 system algebra, separable, well, nowhere scattered, stable rank 1 system algebra, well, nowhere scattered, I'm not going to define what this is. If you were here last year, then you know. But just let me say that this is a huge class of system algebras, which contains all simple non-elementary system algebras. So in particular, this includes the simple case. So assume this, then for every element in the double dual, confine a map, an element that realizes F as its rank. But not only that, you can actually ensure that this element is going to be solved. So this is where softness appears. So when you try to realize ranks, or rather, when you try to realize functions as ranks, then you can, I mean, it's not just that you can do that, but you can actually realize those functions as ranks of very specific elements, mainly elements that are soft, which I will now define. So this is something that happens, not just in the simple setting, but also in the general setting. And so to define that, let me give you a bunch of equivalent conditions, and any of those is going to be what softness means. So proposition let A be a stable rank 1 sister algebra. Let's take some element A named plus. Then the following are equivalent. The first one is that for every positive epsilon, you can find some n in n, so some natural number, such that n plus 1 A minus epsilon plus is bounded by n times e. I will make a bunch of comments once I finish writing the whole proposition. But for now, let me just say that this condition, in essence, says that if you take something that's very close to A, so an epsilon cut down of A, you are actually not that close when it comes to the Kuhn semigroup. Because below n times A, it's not just that you have n times the cut down, but you actually have n plus 1 times the cut down. So you are making a lot of room when you cut down the element. Now, the second condition is also something that's stated in terms of the Kuhn syndrome. And what this says is that for every positive epsilon, as before, there exists some T and C over A, such that A minus epsilon plus T is bounded by A, and B minus epsilon plus bounded by a finite multiple of T. Well, this is an equivalent condition to the one that I just gave. And then another thing that's equivalent, and this is in sister algebraic terms, is that 0 is a limit point of the spectrum of A in every quotient where this makes sense. So in A mod Y, whenever A is not in I, because, well, otherwise A is 0 and 0 is not a limit point of itself. So whenever A is not 0 in the quotient, 0 must be a limit point. So under a stable rank 1, these three conditions are the same. And you can take any of these to be the definition of softness as defined 5 years ago. Mainly, the actual definition of softness, as it was stated, is this one. So this is the original definition of softness, and this is due to Antoine Pereira and Thiel from 2018. And so, as I said in the beginning, for a stable rank 1 sister algebras, this definition is enough. So it's well behaved and everything works wonderfully. But it's conceivable that when you don't assume stable rank 1, this is no longer as well behaved as you want it to be. And it turns out that it isn't. And the proposed new definition of softness in the general setting is this one. So this is the new definition. So that solves one of the two things. And I will explain now why, of course. But the other thing that I also mentioned is that you wanted a sister version or a sister analog for softness. So by looking at this, you'd say, well, maybe this is the notion that you're looking for. Or maybe this is the sister version of softness. But it turns out that very much like 1, this is not as well behaved as we want it to be. And so this is not what we want, but this actually has a name. And this is known as pure positivity. And it's something that Pereira and Toms defined in 2007. Okay. Of the spectrum. of A plus 1. Yes. So you look at the spectrum and you try to see if 0 is something. So this is the setting in the stable rank case. But now when you move to the non-stable rank 1 case, then things change slightly. So this at long last is the end of the introduction. And so let me give you the three-star algebraic definition of softness that Hannes and I propose. This? So? So this is the epsilon cut down of A plus T, which is an element that you find, is bounded by A. T is an element in the Kuhnsen group. It's an element that you find somehow. And then the cut down is bounded by n times T, so a finite multiple of T. So section 2, soft elements. So definition. Let's take a positive element in a system algebra. Then we say that A is soft if the hereditary subsystem algebra has no unital quotients. So has no non-zero unital quotients. So this is the notion of softness that we propose. And well, as I will state in a second, this actually coincides with all these things when you have stable rank 1. So some examples. Well, first, a non-example. A projection is never soft. Unless it's 0. Simply because you fail from the get-go, because the hereditary subsystem algebra of projection has a unit, which is the projection itself. So it's not just that you can find some quotient where you have a unit, but the actual hereditary subsystem algebra is unit. So informally, soft elements will be elements that are really far from being projections. That's the main idea. And as a positive example, one can show that stable elements are soft. So a positive element is said to be stable if its hereditary subsystem algebra is stable. This is a definition, maybe it's 20 years old or something like that. And so in particular, if the hereditary subsystem algebra is stable, then it doesn't have a unit, and neither do any of quotients. So any stable element is soft. And you can think also that softness is generalizing this notion of stability for elements. So let me also give you a characterization of softness, which hopefully can also help picture what these sort of elements we are working with. So if you take a positive element, then one can show that A being soft is the same thing as the following happening. So A is in the ideal generated by G epsilon of A for every epsilon. Where G epsilon of A is the bump function at epsilon. So it's epsilon, it's the identity up to epsilon, and then you go linearly to 0, and then your constant is 0. So essentially what this is saying is that soft elements can be recovered by a very small part of themselves. So A is like the identity function. And what this says is that if you take something that's very small, but which still comes from A, you can actually get the whole thing. You can actually get A. And so, as I said, something that one can prove is that for stable rank 1 system algebras, you are not losing anything. So if you have stable rank 1 sister algebra, then an element A is soft even only if it satisfies one in star, and I should have put and start in the proposition. But what I mean is that the three conditions that I gave before are the same as this condition of softness. So in the relevant cases where there is a bunch of theory already developed, mainly in the stable rank 1 case, we are not losing any information. So the things that were done then still apply now. Now the point now is that if you don't have stable rank 1, you can say most things. And for example, one of the things is that you can relate this notion of let's call it C star softness with this new definition of softness, of softness for Kunz classes. So, oh yes, I should have this proposition. Yes. So, well, recall that now, even some element in the Bunsen group, one says that X is strongly soft if X satisfies 2 in the position. And we add this adjective just to distinguish it from the notion of softness that had already been defined for Kunz classes. So one says that the class of an element A is soft if this is satisfied. So if for every epsilon there is some t such that A minus epsilon plus t is bounded by A minus epsilon plus is bounded by a finite multiple of t. And so what's the relation between the definition of softness that I gave for positive element in system algebras and these ones? Well, one can show that in any system algebra, if you have some positive element, then, well, let's say that A in A, then if A is soft in the C-star sense, then its class is strongly soft. And in some sense, conversely, and we will talk about the converse in a little bit, if the class of A is strongly soft, then you can produce an element that's legitimately soft, which is related to it. Mainly, what you can prove is that then for every positive epsilon, there exists some element in the hereditary subsystem algebra of A, which is soft in the system algebraic sense, and such that it's almost full here, meaning that the following happens. So when such that the epsilon canton of A is in the ideal generated by V. So if you have an element whose Kunz class is strongly soft, then informally there is a full soft element in its hereditary subsystem algebra. In fact, it's only an approximate full element, but you still get this. And this is not a converse to this, but it's still enough for the things that we want to do. So let me just mention a thing about the converse. Yeah.
3 by 2 by 1.
No. 2. Oh, I just erased it. Okay, so 2 implies 1 generally, without any assumptions. 1 rarely implies 2, unless you have stable rank 1 or some sort of cancellation property. And then 2 implies 3. I'm almost convinced. So about the converse, so the converse of 1 fails. So remark if A is soft, this may not imply, or at least not generally, that A is. This is true in the stable rank 1 case, because again, we have all those equivalences. But in general, this is not true. And an example of this, and I'm not claiming this to be trivial, but just something that one can prove, is that you can take A to be a properly infinite projection. Because what you can prove by looking at the definitions, and again by proving something, is that if you have a properly infinite projection, then the Kunz class of that is going to be strongly soft. But it's never going to be soft because no projection is soft. So one doesn't expect this implication to hold. This works in the stable rank 1 case because there are no properly infinite projections. But as soon as you leave that setting, then this is no longer true. What might be true, and this we do not know, is that maybe if A is strongly soft, then A is equivalent to B, and B is, this might happen. And this is true for properly infinite projections. So this counterexample is not a counterexample. So, well, all I'm saying here is that theorem might be improvable, but for now, what we have is enough. Okay. So now, very quickly, let me just say why we want these elements and how we use them. So this is section 3. It's about abundance of soft elements. So what I'm going to define is a class of sister algebras that has many soft elements, but not many in the sense of dense. Okay. So the definition is that A has an abundance of soft elements if, and this has appeared before, if for every A and epsilon, you can find a soft element in the character subsystem algebra of A, such that A minus epsilon is in the linear span of B. So informally, having an abundance of elements, soft or any sort of elements, means that for every hereditary subsystem algebra, there is an element in your class that's close to being full. And this is not the same as density, not even if you're looking at abundance of projections. So this is not the same as real rank 0 for projections. So this is something that's generally weaker, but it doesn't really have a direct relation. So it's not like density implies this or the other way around. So what we can prove in this case and that's the last result. So is the following. So if you have a sister algebra, then the following are equivalent. So one, it has an abundance of soft elements. Two, and maybe surprisingly, it has an abundance of elements whose every cut down is soft, and this is not trivial. So it's not just that we have elements that are soft that are abundant, but we have elements A such that A minus epsilon plus is soft for every epsilon. We also have, and this I'm not going to define, but that the Kuhn semigroup has an abundance of strongly soft elements and well, and this is the whole purpose of the project, is that A has an abundance of square zero elements. So elements whose square is zero. And this in the literature is known as the global clean property. And well, let me just mention that whenever you work with sister algebras, not necessarily simple, that are sufficiently non-commutative, whatever that may mean, this is a property that always pops up. So it's an extremely important property when you try to generalize results from the simple setting to the non-simple setting. So this characterizes in another way what the global clean property is. So in particular, in this setting, when you have the global clean property, you can use soft elements to compute a bunch of sister algebraic invariants because you have an abundance of soft elements. So why is this useful? And this is the part with Ali. So why is this useful? Well, you can prove that the dual of the Kuhn semigroup, so informal dual, is just the dual of its soft part. So you can reduce to the study of soft elements when you're looking at functionals, which is the same as looking at traces for exact sister algebras. You can also prove, using this essentially, that the radius of comparison of a sister algebra is the same as the radius of comparison of its soft part. And you can prove many other things. You can show that the Kuhn's covering dimension of a sister algebra is the same as the Kuhn's covering dimension of its soft part. Not only this, but you can show that any rank, so given any x, if you take its rank, then it's actually the rank of a soft element. So whenever you work on the rank problem, you can assume from the get-go that you're working with a Kuhn semigroup whose every element is soft. And this helps a lot because soft elements satisfy certain properties that are not generally satisfied by all elements. So it's a huge, let's say, reduction to a specific case. And so that's currently where things stand. Well, that's all I wanted to say. Thank you very much.
Question?
I have a question. So this dual is not really a dual because it's
No.
not in the semigroup class. So
Yes.
what fails? Why is it?
It fails O2, which is that every element is the supremum of a way below increasing sequence. This you cannot do. So this is a monoid, so it's a set with an addition and an order, and every increasing sequence has a supremum. this is true. So what fails is this second thing. I think that that's the only reason why we don't call this CU A star.
Any other question in online? Okay, so I also have a couple of questions. So following up Karen's question, so we know that the double dual is a Kunsemi group.
Yes.
The dual is what would be called DCPO.
Yeah.
Sequentially DCPO. So why don't we? And it's a weaker notion of Kunsemi group. So why don't we work this V star and V star star in this weaker category of object that we know?
I don't know. That's the way that people have been doing things. But yeah, it just, let's say that in practice, you are using that it's the dual, but you don't want to say that it's the dual because there is all this category of CU semigroups and so on. But that's the only reason.
Yeah, but I mean,
If you drop that, you still get like continuity.
No, that's the issue.
that's the point. You have everything but continuity, but
Right.
still it's something that in the theory has been studied a lot. So,
But continuity, I mean, that's the whole point of the category. That's why Coward, Elliott, and Ivanescu defined it this way.
yeah, and yeah, another question is, so this is nowhere scatteredness and this softness and everything. Like in simple, I mean, in example that are easy and that are non-simple. Like for example, if you take continuous function over one-dimensional compact space, are those only the purely infinite element, or are there other? I mean,
sorry. So if you take what?
If you take the Kunsemi group of the continuous function over one-dimensional compact space.
Yes, then one-dimensional. Then the only soft elements are the properly infinite ones.
Yeah, so it's the infinite. Okay.
Yes.
And do you have an example of an easy system algebra where you have other element than just purely infinite element?
Yes. For instance, in the Kunz, I mean, if you take the Jason-Rosac algebra, every element there is soft. Every element. And in the Jiangsu algebra, in the Kunsemi group, every element that's not compact is soft as well.
But it's soft in the strong sense?
Yes, because it's the same because you have stable rank one. Yes.
Okay.
Yeah. Yes. Oh. That's Tolkien itself. So this is a notion of covering dimension, very much like you have a notion of dimension for system algebras, which is the nuclear dimension. You can define notion of dimension for Kunsemi groups, and that's what this means. So this is well, this is technically dim of CU of A. So this is a dimensionality notion for Kunsemi groups. No, because this is yes.
Okay, any other question? Yes.
That's the point. Yes, that's the point. And that's one of the reasons why we change the definition when we forget about stable rank one. This set, as soon as you have the global clean property, which is a fairly general assumption, is actually a CU semigroup. So it's an abstract Kun semigroup. If this means strongly soft elements. If you take the set of soft elements as defined, for the stable rank one case, then this is no longer an abstract Kun semigroup. And that helps a lot as well. Yes, so that's one of the reasons why we change things.
Any other question?
Is it open to abstract?
We don't know. Hopefully it might be, but I'm not sure. So for instance, I mean, I've sort of mentioned this in passing, but so this is this. So at least in this case, we do have it. But I don't know in general if that's true.
And yeah, to come back to my previous question,
Yeah.
do you have example where the system algebra is not simple,
That you have soft elements?
which are not purely infinite?
Yes, I mean, for any sister algebra with the global Kleene property, that's not simple,
Yeah, which is related to no scatteredness, right? Or-
which is conjectured to be the same as no scatteredness. Then you have
But-
plenty of elements there that are not properly infinite.
Okay, but what are these sister algebras like concretely? That's what I have hard time to figure out.
But you mean the definition or just?
No, an example like that pops
Well,
up
for instance, well, I was going to say purely infinite sister algebras, but of course you don't want that. But any Z stable sister algebra, simple or not, is going to be nowhere scattered. And in there, most elements are soft, not just the properly infinite ones. In fact,
I mean, it would make sense. If you try.
that's the point. Yes, you want to generalize this. So, for instance, oops, this is always nowhere scattered. In particular, this is always nowhere scattered as well, whatever the sister algebra is. So there are many examples of sister algebras.
This,
Yeah.
observation you made.
Yes.
Steve said. I guess it's true. One hand, if you have a stable around one, Z stable sister algebra.
Yeah.
You look at the soft one.
Yes.
It
It's yes.
would be some
Yes.
projection of.
Exactly. Yes. Yeah. As soon, yeah, CU of a tensor W, I think that every element is soft there. Yeah.
Right.
Yeah.
Okay, so if there are no more questions, let's thank the speaker again.